to be the provost for the moment. It's a great pleasure of mine to be here to introduce Professor Ken Ribet of the University of California at Berkeley. Ken received his PhD from Harvard under John Tate, and over the course of his career, he has made pioneering contributions to number theory, especially in the arithmetic theory of modular forms. I can mention for the Modularity three particularly important results, namely his construction with Deligne of the p-adic functions for totally real number fields, his proof of the converse to Herbrand's theorem, which relates Bernoulli numbers to the class groups of cyclotomic fields, and probably most notable of all, his results on level lowering of modular forms, which are central to the proof of Fermat's last theorem, which is the subject of his talk today. Ken is a very admired teacher at Berkeley. He's won that department's Distinguished Teaching Award twice. And if anybody is thinking of teaching linear algebra, his discussion of his efforts with that course is extremely useful, as I can testify from personal experience. He has advised more than 20 PhD students, many of whom have gone on in turn to distinguished careers in mathematics. He was elected to the American Academy of Arts and Sciences in 1997 and to the National Academy of Sciences in 2000. He's held a variety of leadership positions at the American Mathematical Society and has recently assumed the presidency of that organization. And he'll talk today about Fermat's last theorem. So let's welcome Ken.
Hi, everybody. Thank you very much for that wonderful introduction. It's a great pleasure to be here. I haven't been at the University of Connecticut since a long conference that we had here in the summer of 1984. And I've actually known Provost Teitelbaum for decades. And in the audience are people I've known even longer than that, including one of my roommates from college and my second cousin, whom I've known I would say how long I've known my second cousin. So a very long time. And the goal, as Jeremy explained, is for me to talk about Fermat's last theorem. I guess it's kind of telegraphed by these slides. And what I want to tell you is what the theorem is and kind of explain how it got proved and say a tiny bit about the substance of the mathematics that goes into the proof. So that's the goal for today. These slides have a lot of words on them. You can read the slides or not. They're almost prompts for me to talk to you directly. This first one just tells you some of the background that Fermat's last theorem was first formulated, as far as we know, in the 17th century. And it became kind of notorious over time because it was discovered as a statement without a proof, and people tried to establish the proof over the time that mathematics was developing since the 17th century. And then in this kind of amazing blast of kind of activity, the proof of Fermat's last theorem was announced in June 1993 and made the front page of the New York Times. You could say the failing New York Times. I was actually, my name was on the front page of the New York Times. And, my parents get the Times, so they drive away and say, what the hell, what's going on here? So this was kind of a very exciting time in mathematics. And then, history didn't stop in 1993. There was a lot of history soon after when the proof actually got proved. There was a gap in the proof. But beyond that, there were many subsequent developments that grew out of the tools that were developed in the proof, and it really kind of changed a big part of mathematics. So the kind of single name that's associated with Fermat's last theorem, aside from Fermat, is Andrew Wiles, who's now Sir Andrew Wiles. He was knighted, along with Julie Andrews, and I forget which other famous actress, and met Queen Elizabeth. We didn't really know what to say to him, but this photo was taken, I think not by me, in June 1993 when Andrew was delivering his lecture where he announced Fermat's last theorem. And it was quite an unusual situation because in math conferences there are a lot of different people who speak, and it's pretty common for individuals to give one 1 hour talk, and that's it. You kind of in and out, explain what you're doing. And Andrew announced to the organizers before the conference that he wanted 3 talks, which were held during the conference. And the organizers knew him very well. He's an extremely respected mathematician. They said, okay, you can have 3 talks if you have something important to do. And he said, yeah, I think so. And by the eve of the last talk, there was kind of rampant speculation that he was going to announce Fermat's last theorem. And so a lot of people came to the lecture who weren't otherwise at the conference, and many of them, including me, had cameras. So there's at least one photo that you'll see that I took personally, and this one I might have taken, but I think it was probably somebody else. So what I'm going to do first is tell you what Fermat's last theorem says. So you may remember from high school that there's something called the Pythagorean theorem, where you have a right triangle with sides a, b, and c, and a squared plus b squared is c squared. And it's kind of natural to ask when you're in high school whether you can arrange for a, b, and also c to be whole numbers, positive integers. And the normal way to do that is to start with the a and the b, and then you calculate c, and you say, is c an integer or not? You know, so for example, if a and b are 1, that's an isosceles right triangle. The diagonal will have side equal to the square root of 1 squared plus 1 squared, so the square root of 2, and the square root of 2 is not a whole number, as the Greeks found out. In fact, there's even some apocryphal story that someone was killed for kind of exhibiting a number that not only wasn't a whole number, but couldn't be written as a fraction. But occasionally, as people discover in high school, you can make 2 perfect squares add up to a 3rd perfect square. And the first time this happens is if you have 3 and 4, you add 3 squared and 4 squared, 16 plus 9 plus 16, and you get 25, which is a perfect square. And 5 squared plus 12 squared will work out to be 169, which is 13 squared. So sometimes it happens, and sometimes it doesn't. And what you retain from that is that it's at least possible to find a, b, and c such that a squared plus b squared is c squared. And not only is it possible to kind of stumble on a, b, and c, but you can actually make a kind of very systematic study of what the a and the b and the c could be so that you get whole numbers. And what drives that is a little bit of algebra that's described on the slide. If you take any random integers n and m, with n bigger than m, and you take the difference of the squares as one of the numbers and twice the product of the numbers as the other, then by algebra you add up the squares of those 2 numbers I just described and you get a perfect square. And so that gives you a recipe for generating, 3, 4, 5, 5, 12, 13, and so on. And what the Greeks proved is that aside from some rearranging and multiplying everything by a common value, that's all that happens. So they basically solve the equation a squared plus b squared equals c squared in whole numbers. And the idea of taking a very simple equation and looking for the whole number integer, we call them whole number solutions or the fractional solutions, was one of the big themes of Greek mathematics. And there was a particular mathematician named Diophantus whose passion it was to explore simple equations and try to figure out whether or not you could find any or all of the solutions in whole numbers or in rational numbers. Rational numbers means fractions. So this was one of the driving forces of early mathematics, at the dawn of civilization, if you want to call it that. And what's amazing is that that subject still is very important in 21st century mathematics. And, it's not true that all of the problems that Diophantus considered have already been solved. There's kind of still ongoing stuff. And one of the themes of this story about Fermat's last theorem is that a lot of the people in this room, including me and Jeremy and others, kind of work in the subject where you want to try to solve these Diophantine problems of the ancient Greeks using a lot of technology, fancy mathematics that was developed in the 20th and 21st centuries. And, we kind of went on this quest to develop tools to solve equations somewhat blindly, not being sure that we would ever solve the equations. And then, in 1993, we discovered that it was actually possible that the tools that we were building did something. So this was kind of really validating. Now, Fermat himself, well, let's start with that. He kind of asked himself what would happen if instead of having a squared plus b squared equals c squared, you had a cubed plus b cubed equals c cubed. Or a to the fourth plus b to the fourth equals c to the fourth. Might it be possible to take two perfect fourth powers, add them together, and get another? And Fermat realized, at least for fourth powers, that would be impossible. In fact, he proved that if you take two perfect fourth powers and you add them together, you don't even ever get a perfect square. So this is something that we know he discovered, and he actually wrote down some proof of this when he was a mature mathematician. But when he was a younger mathematician, he was reading Diophantus, and he was scribbling notes in the margin, as we were discussing at lunch today. You probably wouldn't be doing that if you had a Kindle or a tablet, but he was kind of writing these marginal notes, his observations as to what he could do in the direction of Diophantus's world. And he stated, in Latin of course, that you could never get a to the n plus b to the n equals c to the n if n is an exponent bigger than 2, 3, 4, 5, and so on, infinite range of exponents. So that was Fermat's little marginal note, which was discovered by his son in Fermat's copy of Diophantus's work on arithmetic. And of course, it's part of the mystery that that particular copy has disappeared. No one knows where it is. But Samuel undertook the republication of Diophantus's work with his father's marginal notes included. So we know from this republication what Samuel discovered, but it's not like you can go to the Bodleian Library at Yale or something and look at all of Fermat's notes. No, we don't have the original copy. So that's kind of a little bit unfortunate. And for various reasons, we now believe that Fermat had no proof when he wrote this marginal note. And not only that, that he realized years later that he had no proof. And that was why he was writing a detailed argument for a to the fourth plus b to the fourth equal a perfect square. It's because he already understood that he was a little bit too ambitious when he wrote this note. But we really have no idea whatsoever what it was that he was thinking. What was in his mind when he had this note. What could his false argument have been? It's just unknown. And because of all this murky stuff, there are there's a stream of people who come forward with the claim that they have rediscovered Fermat's argument. And they, send physical copies to me and other people. They send email to, a cloud of people. They post it on the web. There are they submit manuscripts to number theory journals. There are a lot of people, just a continuing stream, who think that they have proved Fermat's last theorem, just as there are many people who think they have resolved some of the conjectures that Keith Conrad mentioned in his talk 2 hours ago. A lot of amateur mathematicians and people who are just kind of interested in math are attracted to Fermat's last theorem because the statements are so simple that it's attractive to think that you should be able to reason about these simple statements at the same level as the statements. Whereas the proof that surfaced in 1993, as I said, is kind of the opposite. You start with a very simple statement and you wander in the desert for 350 years and you come out with a proof that is completely somehow not suggested by the actual statement that you're trying to prove. So there's a wonderful book. There's a man named Paolo Ribbenboim who has a Wikipedia page, and he's in his early 90s, I think, or maybe in his late 80s. And he was originally Brazilian, had most of his career in Canada, and he wrote two wonderful books on Fermat's last theorem. One of them is an elementary book explaining the type of arguments that one would naturally get. So there's Alvaro, who's holding up Keith Conrad's copy of this book, Fermat's Last Theorem for Amateurs, which, if you get the right person who says, I really believe in very careful proofs, and I'd like to be able to crack this problem just by direct arguments, where can I learn more? That's where you can learn more. In that particular book, it summarizes everything that Ribbenboim knew was possible at the time when he wrote his book, which was probably in the late 1990s. It was after Wiles' proof was announced. And needless to say, if you look for Fermat's last theorem in popular movies and literature, you will find many references. And I happen to like this little still from Girl with the Dragon Tattoo. So the actress's name, I think, is Nomi Rapace. And in the actual book, there is some discussion of her, the character, working on Fermat's last theorem. There's also plenty of Fermat's last theorem in The Simpsons. Many of you know of a writer named Simon Singh who wrote a wonderful book called Fermat's Enigma about the proof of Fermat's last theorem. He was originally a physicist, and then he was a film producer with BBC. And after he produced the Nova video called The Proof on Fermat's last theorem, he decided that writing was really his passion, and he's written a number of books about mathematics and physics and other topics. And here he has Homer doing mathematics, not Fermat's last theorem. Oh, we do have Fermat's last theorem right in the center. There's an equation that looks like, 12th power is adding up to a 12th power. And if you calculate those numbers on a calculator, you add up the numbers on the left, and to the limit of the calculator, you get the number on the right, which suggests that it's kind of a near miss. So it suggests that it's a counterexample to Fermat's last theorem, which would state that there are no numbers like that. And one thing that you can do, if you know how to check for divisibility of a number by 3, you add up the digits and see if that's divisible by 3, and you keep doing that. You'll see that 3987 is divisible by 3, and so is 4365, but the 4472 is not a multiple of 3. And one of the tricks here is that when you add up two multiples of 3, you will get a multiple of 3. So actually, this is a big theme in mathematics, that when you kind of deal with numbers, it's not only kind of their size that matters. You don't want to think of them just as decimals, but you can also very fruitfully think of them when you reduce them modulo some numbers. So that means you divide by the number and you look at the remainder. If you take a number, and for example, if you take 3987 and reduce it mod 7, that let's say mod 10 rather, you kind of throw away, you cast out all the multiples of 10, and you will be left simply with 7 in that case. 3987 modulo 10, as we say, is 7. And this modulo stuff is actually pretty prominent in what I will describe later on. And here's the first taste of it, this business about multiples. There is a long history of proofs of results in the direction of Fermat's last theorem. Partial results, I'll explain what that means in just a second, and also incorrect arguments trying to prove the full theorem. So one of the first names in the story is Leonard Euler, who was a Swiss mathematician from the 18th century. And just as Fermat was able to treat the case of exponent 4, a to the 4th plus b to the 4th equals c to the 4th, Euler did exponent 3, which actually is a lot harder than exponent 2. at exponent 4. And the reason for that is that when Fermat had his argument, basically he could deal simply with whole numbers the entire time, whereas Euler in his argument had to introduce a square root of -3, so an imaginary number, and that makes the argument, at least to non-mathematicians, much more complicated, and even to mathematicians, slightly more complicated because there are more things that you have to check. And a lot of the mathematicians who followed Euler tried to replicate his argument for bigger exponents, and the standard mistake that they made was to imagine that there was no difficulty involving factorization of numbers when they're more complicated than just having the square root of -3. So a lot of people thought they had a proof, and then their colleagues would say, no, 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 that's not right. You have a little subtlety that you've neglected. And so the same author, Ribet, well before the proof of Fermat's last theorem, wrote a book that was really intended for mathematicians, but it's a very entertaining book. So there are 13 lectures in the book, that means 13 chapters, and he talks about different people who stepped up to the plate, if you like the baseball analogy, with different techniques for dealing with Fermat's last theorem. And one of them, for example, is a woman named Sophie Germain. So 2 weeks ago I lectured on her theorem when I was visiting Chicago, Loyola of Chicago, and she had very interesting arguments. And another person who is very prominent in the whole story is the German mathematician Ernst Coomer. His photo is at the bottom of this slide. And Coomer really did a lot of progress in trying to explain how to prove Fermat's last theorem for a variety of different exponents. Although it's not even known to this date that his arguments would work for an infinite number of exponents. There are all kinds of wrinkles in the subject, but it seems that his arguments would work for the majority of exponents. And in something that I consider really kind of remarkable and miraculous, a number of mathematicians got together a couple of decades ago and cobbled together proofs of Fermat's last theorem for every single exponent up to about 4 million. So they used the work of Coomer provides a criterion for Fermat's last theorem to be true. So they used Coomer's criterion, but then more and more complicated criteria of the type that were described in Ribenbaum's book for mathematicians, the previous slide, and using computers, of course, for every possible exponent up to 4 million, they were able to show that there are no integers a, b, and c such that a to the n plus b to the n equals c to the n. So, if you take an exponent like, 144,169, when you say there are no a, b, and c such that a to the 144,169 and so on will be c to the 144,169, you are stating a theorem about all a, b, and c. It's not that you're just making a calculation for some numbers, but nonetheless, by using the criteria of Coomer and his successors, you can prove that theorem. So that's kind of a really amazing fact. One of the things that happened, so I should describe a little bit, when Wiles announced his proof in 1993, all of the science media knew that he was going to do that. I mean, knew is probably a little bit strong, but people were alerted to the fact that this was going to happen. So he made his statement, and it was wild applause, and 5 minutes later there was a phone call from the New York Times. The New York Times wanted to interview him and talk to him about his proof. And he turned to me and he said, "Oh, Ken, you talk to me." So it was actually Gina Clutt, you talked to her. So I dove under a desk, literally. That was the only place where it was quiet enough. And I spoke to Gina Clutt for about a half hour. And our conversation is reported in the New York Times. And somewhere in the article, she said, Ken Ribet at the University of California, Berkeley, who was speaking for Wiles. And then it got to be known somehow that I was kind of his press secretary. You know, right? There, I'm Sean Spicer, right? So, the whole summer of 1993, people were phoning me, asking me all kinds of questions. You know, America's Most Wanted wanted to segment on Fermat last year. And, you know, I was talking to all kinds of people, most of whom did not have, they were not science writers, they were writers and producers in various cases, and they asked me lots of questions that I hadn't anticipated. And one of them is this question of why it's not good enough just to look for all numbers up to 4 million. Doesn't that satisfy you? You know, so of course I tried to explain that there's this concept of a proof where you're proving, you know, for all values and not just for values up to 4 million. And then I tried to remember, at least for myself, that there are situations where you can compute and compute and compute and seem that you find no solutions to something, but in fact there are solutions kind of far away, further than you've computed. And one of the first examples that you can give is what's called Hell's equation, when you look for numbers x and y such that x squared minus a given number y squared is equal to 1. Well, of course, you could get x is plus or minus 1 and y is 0. But aside from that, you know, you wonder about solutions. And it's a theorem in kind of a junior level number theory course that there always will be solutions, but you probably won't, you won't find them for all values of the coefficient of y squared unless you have a systematic method. And in the junior level number theory course, you probably learn a systematic method using continued fractions, but if you just go searching, you don't find it so fast. And the smallest number next to y squared, where you get a pretty big looking first solution, is 109. And Fermat knew how to do this kind of work. And it's very fun, this example, I think, that you have to go so far out to get the first x and y. And another thing that became kind of very well known in the 1980s is an article written by Noam Elkies, who at the time was, you know, a wunderkind. He'd written the shortest math thesis in history, and he was named full professor at Harvard right after, because he solved a famous open problem. And he looked at an equation that Euler had advanced. Euler had already proved that, you know, a cubed plus b cubed equals c cubed didn't have solutions other than, you know, one of the numbers being 0. That's what he did in the 18th century. And he had the idea that when you raise the exponent, you can also raise the number of variables. So for cubes, you just have 3 variables, a, b, and c. And for fourth powers, you should have 4 variables, a, b, c, and d. So he said, well, by analogy with what I've proved, there should not be non-zero numbers, a, b, c, and d, where the sum of the fourth powers of the first 3 is the fourth power of the fourth. And so this became Euler's conjecture. And by the time I was a graduate student, I think most people were convinced that Euler was incorrect, that his conjecture was false, but people didn't know exactly kind of where to look for a counterexample. And Elkies, using one of the earliest laptops, Toshiba laptop, I think, was kind of the first person to realize where to look for a counterexample. And he did a very short computation, and he uncovered this one that starts with 268, 2440. So, you know, it's quite remarkable that using a kind of targeted computation, you could prove the falsity, you could disprove a conjecture from the 18th century. There are actually smaller counterexamples that were found later by exhaustive search, but this is the first counterexample that was discovered, and that's Elkies' numbers. So now I'm going to turn to the main subject, which is kind of the story of the proof of Fermat's last theorem as it kind of unfolded, starting, I think, you know, around 1980 or so. So here's a photo of a guy named Gerhard Frey, who's one of the principal names in the story that I'm telling. So he is a mathematician. When I knew him, he was in Saarbrücken, and he then moved to Essen in Germany around the time of Fermat's last theorem, and I think he's now a professor emeritus there. And I took this photo of him in Barcelona, and he started talking to various people. He had an idea, and this is an idea that he could not justify himself, but he thought it was a really good idea, and he thought that by talking to specialists, including me, I was just one of many, that he would kind of connect up with somebody who believed in his idea and would turn it into a mathematical result. And his idea was that if Fermat's last theorem was wrong, then there would be a very well-known conjecture, the kind of number theory that Jeremy and I, and many other people in this room actually studied. I call it the modularity conjecture for convenience, that conjecture would be false. So, just logically, if Fermat's last theorem is false, then this other conjecture is false. And what that means is that if this conjecture is true, which everybody expected, then Fermat's last theorem would also be true, which at the time, people were a little skittish about. I mean, my attitude was, when I was a graduate student and postdoc, here's this funny equation, a to the n plus b to the n equals c to the n. Why should it not have solutions? There's kind of no kind of theoretical reason why Fermat was going to be right. And there was no way to kind of deal with the equation fruitfully. Maybe it was like this conjecture of Euler, where you just, somewhere there's some huge counterexample, and it actually isn't true. So I didn't know. And I certainly didn't want to work on the problem because I had no guarantee that I'd produce anything useful. So Fermat's last theorem to me was kind of like, I don't want to touch it. And here was Frey saying, if you believe in modularity, which I'll explain, then you also had better believe in Fermat's last theorem. So that was, quite a statement. And I will confess that when Frey first explained this to me, he was visiting Berkeley one day in the early 80s, I think. I wasn't so convinced that Frey was right either, but I certainly listened to him, and it was an interesting idea. But not much happened initially. And I won't talk too much about this particular slide, where I explain that this modularity conjecture had various names associated to it. And in order not to dwell on the names, I'll just call it the modularity conjecture. But it was proved. It was proved in the 1990s, so now it's the modularity theorem. And because it was proved, and because Frey's idea was translated into correct mathematics, that's why we know Fermat's last theorem. Right? So this is kind of two central things. The modularity conjecture was proved, and this link was made. That's how we know Fermat. Okay? And here's a slide with a lot of dates and statements. So I'll just try to kind of explain that Frey came around and tried to tell people that you could probably make a link between the modularity conjecture and Fermat's last theorem. So as I just explained, he said that to me, he said that to other people. He didn't get a lot of traction until he began lecturing to kind of conferences, get 40, 60 people and explain this to them. And people started saying, maybe this is right. Maybe we can convert this into an actual proof, Frey's idea. And by 1985, there was a mathematician named Jean-Pierre Serre, who was, as I said earlier today, one of the greatest living mathematicians now, certainly one of the greatest names of the 20th century. And Serre kind of looked at Frey's 3-page manuscript and thought about it, and he distilled something very precise. He said, you can actually make Frey's link work. So Frey was positing a link between the modularity conjecture and Fermat's last theorem. He said, you can make this link work if you could just prove one additional thing, which was kind of right in my subject. So Sayre called it epsilon. Epsilon is used in math to denote a small number. And Sayre had the impression that this epsilon that he was formulating was something, well, he himself didn't know how to do it, but he was betting that the specialists in the subject, specialists for him is kind of a pejorative word. It's like, people who kind of live in a hall and think about nothing else, that the specialist would just prove his epsilon, by return mail. And so I actually listed by proved epsilon, but it took kind of a year. And the fact that no one did it right away, and the fact my actual proof, which was quite voluminous, is pretty good evidence that epsilon was not as small as Sayre thought. It was pretty hard, but I proved it. And I started telling people in 1986 that I proved it. And for various reasons, which maybe make a separate story, it took about 4 years before the thing actually got published in a journal. One of the reasons is that there were a number of prominent people who were openly skeptical that I'd actually proved what I said, but I gave lectures on it. More and more people got convinced. The argument was clear enough. And all of the little intricate pieces of the argument got written down, and the proof stood. But then, as you can see, for example, in this NOVA video, which was made around 1995, when Andrew Wiles heard that I had established this statement that Sayre called epsilon, just as everybody kind of had good faith in Wiles when he said he wanted his 3 hours of talks, Wiles had complete confidence in me, and he kind of said, okay, well, Ribet proved this thing, and I'm going to try to prove the modularity conjecture, and therefore prove Fermat's last theorem. So what he did was he kind of snuck away to his attic in Princeton and sat for hours and hours and hours and hours, I can't imagine how many hours, over a period of 7 years, working at night, working in weekends, trying to figure out how to prove modularity. And in 1993, he came down from the attic and gave these lectures in Cambridge, England, where he said that he had done it. And what is kind of amazing is that, if I had had an idea to prove this modularity conjecture, which, as I said, is one of the biggest conjectures in the subject at the time, I would have proved the modularity conjecture. This was a major thing. And Wiles said that it was only because of the link to Fermat that he was kind of willing to go out on a limb and work for 7 years on this conjecture. But the modularity conjecture itself was not a sufficient prize for him. And he kind of explains that as a child he had been motivated by Fermat's last theorem. He read about it in the book. And the idea of actually proving that statement was what enabled him to work for these 7 years and come up with a proof. But then, it's not quite announced in the slide, but after Wiles gave his lectures, he distributed his manuscript to about 5 people who were supposed to be referees for his manuscript, which he submitted to one journal. It's called Journal A. And one of the referees, a colleague from Princeton, immediately found a problem in the chapter that he was reading. And this was the famous gap that was lurking in this manuscript for literally a year, over a year. Wiles, it just wasn't clear at first whether this gap was very important, was it a major gap, or just a little blemish? What do you have to do to complete it, complete the proof? And Wiles brought in Richard Taylor, who's now a professor at the Institute for Advanced Study in Princeton. And Richard Taylor and Wiles worked together, and they completed the proof by making a separate argument, replacing the part where there was a gap. And they ended up with 2 manuscripts, Wiles' original manuscript, and then the Taylor-Wiles joint paper, which was kind of alongside it. And these 2 manuscripts were published together in Journal B. They kind of forgot about Journal A. So Journal B, which is the Annals of Mathematics, published the 2 things together. And then there's a technical thing, but a very important thing, which is that in Wiles and Taylor and Wiles, they didn't quite prove the modularity of all the elliptic curves for which there was the conjecture, but just enough to give Fermat's last theorem. And the modularity was settled completely over a 4 or 5 year period by a number of people who worked very hard to extend the power of the arguments that Taylor and Wiles had. And among them is Brian Conrad of Stanford University, who is related to one of the people in this room. So I think you know Brian Conrad. There's also Richard Taylor, Fred Diamond, and Christophe Roy. Okay, so modularity was proved. So modularity became a theorem in 1999. And what I will try to do for a short amount of time is try to give you a flavor of what this modularity is about, and also what it has to do with Fermat's last theorem. So that's a tall order, but at least I hope to give you some sense of what's going on. So even going back to Diophantus, you can look at equations that are a little bit more difficult than just a squared plus b squared equals c squared, which the Greeks solved completely. And the simplest one would be y squared equals x cubed plus 1. So that says in words that you take a perfect cube and you add 1 to it and you get a perfect square. And you could ask for solutions in whole numbers, positive or negative, or in fractions, positive or negative. And I'll tell you what all the solutions are. So, if you're a mathematician, you start with 0, so you can let x be 0, and then x cubed plus 1 is 1, so y could be plus or minus 1. If you're a really strange mathematician, you can take x to be minus 1, and then x cubed is also minus 1, so x cubed plus 1 is 0, and then y could be 0. And if you're creative type, you can take x to be 2, 2 cubed is 8, and you add 1, and you get a perfect square, 9. So y could be plus or minus 3. And it turns out that those are the only solutions to y squared equals x cubed plus 1, not only in whole numbers, positive or negative, but also in fractions, positive or negative. So that's really great. So here's a cubic equation, and you can deal with that cubic equation completely. You can find all its fractional solutions. But you can have, more complicated cubic equations, like y squared equals x cubed minus 17x minus 3. I just wrote down, I don't remember why. Or y squared equals a cubic. You don't need a term with x squared, because you can make a little change to get rid of the x squared term using algebra. But you take an a and b, pretty much a and b work. Every a and b will work, and you have a little cubic equation. Just take a and b to be integers, whole numbers, and you can ask questions like, are there only a finite number of fractional solutions? Can you list them, if there are? Can you tell whether or not there's a finite number? And these questions, believe it or not, are kind of at the frontier of Diophantine mathematics even now. There's not, like a completely algorithmic solution that infallibly tells you the answer in a time that you can predict in advance. Now, in fact, this is a slight digression. There are a lot of computer algebra programs out there. Mathematica is probably the best known one, or Maple. And you can give these algebra programs the data of a pair of numbers A and B, and ask for the number of solutions. And in practice, those programs will give you the correct answer. But there's the possibility that you kind of hit return and see what happens, and you come back 3 weeks later and the thing's still running, and you couldn't have predicted that, and you don't get an answer. So we don't have a full control over these cubic equations, which are called elliptic curves for some reason, even when you ask the simplest possible questions. And another thing that reporters ask me is what the thing had to do with ellipses, and the answer is there are these things called elliptic integrals in calculus that you get when you try to measure the length of an ellipse from one point to another. And elliptic curves are based on elliptic integrals. So that's That's why they're called elliptic. And if you do a Google search on elliptic curves today, you'll probably get very quickly to cryptography, because elliptic curves are used as some way of making problems that would be otherwise fairly easy into quite difficult problems, in the sense that you need a lot of computing power to unravel them, at least if you don't have a quantum computer, which no one has so far. And if you have a little key fob to open a car, or even cell phones, a lot of electronics nowadays are based, the security involved in the transmission is based on elliptic curves. So elliptic curve cryptography is kind of completely a central subject, and it's based on these elliptic curves when you combine them with congruences. So congruences came up already in Keith's talk 2 hours ago, and they're about to come up here. But first I want to show you a photo. So the guy on the right is me. That was the summer after I got my PhD. And the guy on the left is Girish Morra, who is now a professor emeritus at Princeton. And Morra is one of the names that I kind of skipped over a bunch of slides ago when I was talking about modularity. He has been very vocal about the fact that he formulated a precise conjecture involving modularity before anybody else did. And there's a slight difficulty, which is that he didn't tell anybody. But nonetheless, he certainly was a great master of modular forms and elliptic curves, which are the subjects that I'm talking about. And a lot of his ideas are still, completely central in the subject. So now I'm going to tell you what Fry did, which is basically one line. So remember, an elliptic curve is just, y squared equals a cubic. And Fry said, if you have a solution to Fermat's equation, suppose A, B, and C are positive numbers, then we're going to write down a cubic. Y squared equals x times x minus a to the n times x plus b to the n. And you could say, well, wait a minute, what happens to C? Well, the point about C is that this elliptic curve will be special because a to the n plus b to the n is a perfect nth power. And you don't have to have C written explicitly in the formula for the elliptic curve. And what Fry kind of understood in some sense, not in a sense of mathematical proof, is that that elliptic curve, the elliptic curve given by that equation, could not satisfy the modularity conjecture that we all then believed in. And what I proved precisely is that that elliptic curve does not satisfy the modularity conjecture. And what Wiles and his successors proved later on is that all elliptic curves satisfy the modularity conjecture, so there's, kind of a contradiction there. And the contradiction is that you could not have had the A and the B such that A to the n plus B to the n is a perfect nth power, because if you did, you'd get an elliptic curve with a property, with two competing properties that kind of rules out what you've done. So, this is a hard sell. You guys are my friends, right? So, but imagine talking to a reporter and say, well, you cannot write down this elliptic curve. And they'll say, well, you just did, right? So what's going on? Well, you write down the elliptic curve, but the elliptic curve has a property stemming from the fact that a to the n plus b to the n is c to the n, and that property, if you like, you can prove is not possible. So there's a lot of funny business. And what we have to do now is just have, a kind of short conversation about congruences, right? So congruences occurred when I talked about the Simpsons, when I talked about being a multiple of 3, right? And if you take a number, you can divide it by 3, and you get a remainder. So the remainder is 0 if the thing is actually a multiple of 3, but otherwise it will be 1 or 2. So you have a remainder when you divide by 3, and that remainder is the integer mod 3. So for example, if I take, 172, and I use the trick of adding up the digits and stuff, I'll discover 172 is 1 mod 3. And if I take 2017, that'll be 1 mod 3 also, because 2, 0, 1, 7 add up to 10, 1 and 0 add up to 1. That's the trick. You get it's 1 mod 3. But you can take another number. I'm mostly going to take prime numbers. Take a number 7. And every number is something mod 7, and the possible somethings are 0 up through 6. It's the remainder on division. And sometimes you get paradoxical results. For example, if you divide 7 into -1, you'll discover the quotient is -1 and the remainder is 6, which surprises people. The remainders have to be 0, 1, 2, 3, 5, or 6. It can't be -1. And basically, two numbers have the same remainder if their difference is a multiple of 7. So -1 and 6 are the same thing mod 7. They have the same remainder because their difference, which is 6 minus -1, will be 7. And that's a multiple of 7. So there's this kind of machine. When you have a number, p is a prime number, like 2, 3, 5, 7, 11, whatever. That's the modulus. And when you take a number mod p, you get a remainder that's between 0 and p minus 1. There are p possible remainders. And congruences occur in lots of normal life. So for example, if you were to take your entire fortune and convert it into cash and try to have the fewest number of pennies, the number of pennies in your pocket would be 0, 1, 2, 3, or 4. It would be your kind of net worth mod 5, net worth in cents, modulo 5. And then there's military time, regular time, and so on. So another thing, just this is a slight digression, but it's relevant if we go on some more, is that if you take numbers mod 4, 4 is a good number to divide by, the possible remainders are 0, 1, 2, and 3. There are 4 possible remainders. If you take the prime numbers, 2, 3, 5, 7, 11, and you look at them modulo 4, well, of course, 2 has remainder 2, and 3 has remainder 3, but the numbers beyond 2 are all odd. So the remainders will work out to be either 1 or 3. And if you take a prime number bigger than 2 mod 4, it's either 1 mod 4 or 3 mod 4. And you can make statistics. Keith was doing this kind of thing in his talk. And you'll discover, if you do counts, that as you go up to more and more primes, kind of roughly half of them are 1 mod 4, and the other half are 3 mod 4. And there's a famous theorem of Girish Morra, who was also mentioned in Keith's talk, that this is really true, that if you take the ratio as you go out toward infinity of the primes that are 1 mod 4 relative to the primes that are 3 mod 4, the ratio of that will approach 1. So you could say heuristically that if you take a random prime number, the probability that it's 3 mod 4 is half, and the probability that it's 1 mod 4 is also half. It's kind of like flipping coins. So what we're going to do is we're going to take an elliptic curve, and we're going to kind of work on the elliptic curve mod p, and what happens will be different whether p is 1 mod 4 or whether it's 3 mod 4. So I don't know how many, if you have much stamina to go further, but we'll try a little bit. So the simplest elliptic curve that I can think of, it's supposed to be y squared equals x cubed minus or plus ax plus b. I'll take y squared equals x cubed minus x. So that is a very simple choice, but it turns out to be a very special choice. There's a lot of symmetry to this particular example that was already known to Gauss. Gauss is another person Keith mentioned in his talk. So we're going to take this elliptic curve, which is one of the simplest you can imagine, and you take a prime p, and then what you do, instead of looking for solutions to y squared equals x cubed minus x in actual numbers, you look for solutions where the two sides just have to have the same remainder mod p. So that means if you think of the two sides as whole numbers, they're different, should be a multiple of p. And the way you do this count is you just kind of shrink your world. Instead of having all numbers, that's an infinity of numbers, you just take numbers 0 up to p minus 1. And those are the only numbers that count in your world. There are p possibilities for x and p possibilities for y. And you ask, among the p squared pairs, x, y, how many of them satisfy y squared equals x cubed minus x, where multiples of 3 don't count. And you get a number that depends on p, and that number is n of p. And if you want, these slides are available on the web. I'll write the URL in a second. You can bring these up and try to verify that if you take the prime to be 5, there are 7 solutions. And you can take prime to be 7, there are also 7 solutions. You can do a few more examples, and you can make a table. So here's the table I made, where I take the different primes, which are thought of as moduli. You're going to work mod p, mod 3, mod 5, mod 7, mod 29, mod 41, and so on. And for every prime, you look at y squared equals x cubed minus x as a congruence. You just think of everything in the world with numbers mod p, and you count the number of solutions. And this is something that Gauss did in his diary. So this is called Gauss's last entry problem, because it's at the very back of his diary. And you will get data like this. It's very helpful to have a computer where you can do this for larger and larger primes p until you get tired. And you'll see that a lot of times the bottom number is the same as the top number. And what you'll discover pretty quickly is that the bottom number is the same as the top number exactly when p is 3 mod 4. In other words, 1 less than a multiple of 4. For example, 19 is 1 less than 20. 31 is 1 less than 32. 23 is 1 less than 24, and so on. And then those primes are kind of easy. You can see the numbers will coincide. If you do, undergraduate number theory, you can prove that they coincide. But the primes that are 1 mod 4 are completely different. In fact, the bottom number is never equal to the top number, like 7 is not 5, 15 is not 17, 39 is not 37. And you'll see that it looks like, sometimes the bottom number is bigger than the top number, and sometimes it's smaller than the top number. It's never equal to the top number. And you can make all sorts of observations if you just want to do some numerics. For example, take the difference between 41 and 31, which is the right-hand number. That difference up to sign is 10. 37 and 39, the difference is 2. 15 and 17, it's 2. There are a lot of 2's, I guess. But what happens is that difference is twice an odd number, which could be plus or minus, and it's never very large. So there's a theorem of Hasse. Hasse was also mentioned in Keith's talk 2 hours ago. One of Hasse's best-known theorems tells you that difference can't be very large, and there it is on the screen. In fact, it's twice an upper bound for how big it can be is twice the square root of p. So if p has 6 digits, square root of p basically has 3 digits. It's a much smaller number. And what Gauss did, I think I'll stop here, was to make a completely precise formula for that difference for primes that are 1 mod 4. How do you know that the difference is minus 2 in the case of 17 and 15? How do you know it's minus 10, 41 and 31? How do you know it's plus 2, 37 and 39? Well, Gauss has a formula. And part of the formula, I'll just say a tiny word about his formula, is that if you take a prime that's 1 mod 4, like 41, it will be a sum of two perfect squares. This is something that Fermat proved in the 17th century. So for example, 41, I think, if I'm not mistaken, is 25 plus 16, right? 17 is 16, 1 plus 16. And what Gauss proved is that you take the odd number and you multiply it by plus or minus 2, and you get the difference. So for example, 41, sorry, this is probably going too fast. 41 is 25 plus 16. The odd number that you're squaring is 5. And twice 5 is 10, which is like the difference. But the difference here is kind of minus 10. How do you know it's minus and not plus? Well, Gauss found that out as well. Gauss gave it, just crushed the problem. He solved it. And that's just for one elliptic curve. The elliptic curve, y squared equals x cubed minus x. And then you could say, well, come on, Gauss was a long time ago. Suppose you have another elliptic curve, y squared equals 29x minus 34 with an x cubed. What's the formula then? And the answer is that it's not possible to have an explicit formula where you give a completely simple recipe, but you can give a formula in a more generalized sense where you connect up the numbers that you get by calculating solutions mod p to something completely different, another subject, which is the subject of modular forms. And the idea is that you make a table of modular forms, off in one room, and you take your elliptic curve in another room, and then you kind of look at the two things, and every time you have an elliptic curve, you're going to find a modular form on your table that corresponds to it. And this was kind of observed starting in the 1950s by various people, but it was proved only in 1994 by Taylor and Wiles, and then in more generality by the people I named later on. So this is quite an amazing thing that you start with congruences and you get a connection to modular forms which belong really to the world of calculus. It's clear when we're doing these counts, it's kind of algebra. And algebra and calculus are supposed to be completely different subjects in mathematics, but modularity connects them up. And this was an amazing moment in mathematics, having this bridge built between the two subjects. And there have been lots of generalizations and lots of subsequent developments that I won't go into. I do want to say one more word about the news media. Everybody was asking about practical applications. And so far, there have not been practical applications. But if you look at the many, many practical applications of mathematics, you will discover over and over again that subjects that were introduced for completely theoretical, curiosity-driven purposes have turned out to be incredibly useful in the 21st century world. All right, so I'll stop there.
So thank you very much. Are there questions?
Great. We got a question. Do you have any idea of how many entries Gauss had in his notes?
So, I'll kind of explain. The answer is no, but I'll tell you kind of how I kind of came to this, which is that one of my favorite books in the world is called A Classical Introduction to Modern Number Theory by Ireland and Rosen. When I was an undergraduate at Brown in the 1960s, Ireland and Rosen were professors there, and they taught a course that became that book. And one of the really driving forces behind the course was that the Brown Science Library had all sorts of original manuscripts. And they would go and consult the works of our forefathers in mathematics and see what they actually wrote. And they discovered a lot of things that were not kind of well known among mathematicians who were working in the 1960s. So the book was kind of really a great revelation to me. And I imagine nowadays that there's no difficulty in actually consulting Gauss's diary if you want to do that. It's probably written in Latin.
Is there a way to get to find near misses to things like Fermat's last theorem? Like if you want to find things like Homer Simpson is looking at, you know, maybe
Yeah,
the fifth plus
so-
maybe the fifth.
I don't know the answer either. These are great questions. You know, so suppose, for example, you were a writer for The Simpsons and you wanted to generate a lot of near misses. How would you do that? I haven't thought about this question, but I bet there are people who know a lot about